To help prepare you for the test, I'm going to do a really quick review of the practice test that we didn't get too much time in class to work on, so use this video to better prepare yourself for the test. I'm going to scroll down actually to the end, and I'm going to work on this document from the last problem up, because we did a lot of the earlier problems in class. Starting with the last problem, we have a ball is rotated on a string on a vertical circle. So if we draw the vertical circle, like so, and we have a ball on a string, and what is the acceleration vector when the ball is 30 degrees below the horizontal? So actually, bit of a bad wording here because technically that could have been here or about here actually. For this problem, let's go ahead and take this one because this is 30 degrees below the positive x-axis, which is typically what is expressed or meant by when someone says 30 degrees below. So there we go, we have the... Let me zoom into this picture here. All right, we have this ball, and what we're going to do is we need to write this in unit vector notation for the acceleration vector. So first off, we always draw the free body diagram. We got mg going straight down, and we have our tension force going radially inwards. So this is tension. Now, one thing that is not said here is whether we have to use this as our axes, or we could use radially inwards and tangential as our axes as well. As long as it's 90 degrees difference, you can use either for the axes. Either one you use, you're going to have to break one of these vectors up into sine and cosine. You know, you have to break one of the vectors into their, you have to decompose it into the component vectors. So let's say we did the radially inwards and the tangential one. Okay, so that would mean that we have the sum of all forces equal in the, let's say the radially inwards, which I'll need to make a little perpendicular sign, is equal to the mass times the acceleration in that perpendicular direction. And the reason we did that is because that's going to equal mass times the centripetal acceleration. Centripetal acceleration, no centripetal. All right. Well, what is the sum of all forces in the centripetal direction, or the in radial inward direction? It's just going to be tension. However, it's not just that, because we also have a vector that is part of the gravity. So, okay, let's break this component of gravity into a vector that is going tangential to the circle and a vector that's going... Really zoom in on that. So we have a component that's going radially outwards and a component that's going tangential to the circle. So this component right there, that one is the component that's going against this tension force. And this angle and this angle are probably the same. One way we could just double check that is if this angle goes to 0, this is at a 90 degree, it's right here, and that would mean this angle probably also goes to 0. So these are probably the same angle. All right, so that means we have tension minus, so right now we've made radially inwards as positive, tension minus mg sine theta. Oh, sloppy mg sine theta equals mass times centripetal acceleration, which we could, depending on, here it didn't actually say what variables it should be in terms of. So we could have this be omega squared, or we could have this be the velocity squared over r, but actually I realized that this is asking for the acceleration vector, so we're just going to put acceleration in the radial direction. So if we solve for that, we get the acceleration in the radial direction is equal to the tension minus mg sine theta all over mass. All right, now let's do the other direction. So what's the sum of all forces in the tangential direction? That one we only have one force in the tangential direction, and it would be the part of gravity that's going that way. Which, if the other one, if this one was sine, then the other one must be cosine. So we have mg cosine theta equals the mass times the acceleration in the tangential direction. So this would just be acceleration in tangential direction equals g cosine theta. And let's put this all together, but also let's plug in the 30 degrees. So 30 degrees when plugged into sine over here is 1/2. So we have tension minus 1/2 the mass times gravitational constant all over the mass. And then over here, cosine is square root 3 over 2, so we have square root 3 over 2g. All right, so what would the total acceleration be? The acceleration vector would be, if we do the radially inwards first, this would be the acceleration in the radially in direction, so that one, and we're going to put an I hat on that, plus the tangential direction, and that's going to be with a j hat. So that's going to be like a j hat. All right, so that equals the tension minus 1/2 mg over m, and that's going to be I hat plus square root 3 over 2g, j hat, and there's your answer. All right, moving on to the next one. We have a metal sphere is dropped in the ocean. The force of drag of water can be modeled as this equation right here. Set up a differential equation. This one's pretty easy. When we say set up a differential equation, we're going to start with sum of all forces equals mass times acceleration. We're going to write out what the sum of all forces is. That's going to be, this is dropped in the ocean, so there's a force of gravity going downwards, and it's a force of drag going up. So we have beta v squared minus mg is equal to the mass times acceleration. But the acceleration is dv dt, so we have the beta v squared minus mg equals mass times dv dt. And you could rewrite this to be instead, we could do dt is equal to m over beta v squared minus mg dv. So this is acceptable as well as this. All right. But now, determine the terminal velocity if the metal sphere has a mass of 1,000 kilograms and the beta coefficient is whatever that is. So how we do terminal velocity is we're assuming, so for the velocity, when you're dealing with terminal velocity, what you have is that the acceleration must equal 0. So when we're dealing with terminal velocity, acceleration must be 0, which means the sum of all forces equals 0, which then means that we have this beta v squared equals mg. So then we're just solving for v, so v is equal to the square root of mg over beta, and then we just plug in our variables at that point. So the square root of 1,000 times effectively 10 divided by 30. And the units should work out just right, so we'll just trust that will be the case. To give us velocity. So whatever the answer to that is, plug it in your calculator. All right, the next one. Determine how far away a satellite needs to be from Earth so that it remains motionless in the sky. In other words, determine distance for geostationary orbit. For this problem, we're going to start with Kepler's third law, which is t squared is equal to 4 pi squared over big G m times the radius cubed. And what we're doing is we're going to make omega essentially equal to 2 pi radians divided by the time, which is going to be 24 hours, essentially. We need to convert that from hours into seconds. So that would be 3,600 seconds times 24 hours. So I'll just plug it in a calculator really quickly. So that would be 24 times 3,600, I believe. So that's 2 pi radians in 86,400 seconds. That's going to give us essentially that the satellite is going to go one Earth rotation when the Earth does one full spin, one full day. In other words, the period needs to be 86,400 seconds. So that's not our final answer. I shouldn't box that. But that is going to be going into our period equation. So what we're doing is solving for r. So we can just solve for r really quickly. R is equal to the cube root of big G times m times the t squared all over the 4 pi squared. And so that's the square root of 6.67 times 10 to the negative 11th and times the mass of the Earth. So we need to know what the mass of the Earth is, so unfortunately I didn't give that to you in this problem. Mass of Earth in kilograms. It needs to be in kilograms for this. That is apparently 5.972 times 10 to the 24th power, really big. And then we're going to multiply that by the 86,400 seconds all squared, and then we're going to divide by 4 pi squared. So some big numbers up top, but we are taking the cube root of those big numbers, so it should come down a little bit, and then we'll get our answer. So whatever that is, when you plug in the calculator, that's what we get. All right, number 9. If a weight hung by a spring stretches the spring by 0.5 meters on Earth, how far would it stretch on a planet with 3 times the radius, assuming the planet is made of the same material as Earth? So one thing we have to do is we have to figure out what the force of gravity for this new planet is. And so this force of gravity is going to equal just our normal, big G times our mass that we're hanging times the mass of the planet, But the mass of the planet is going to equal some density. We'll just do a rho symbol times the volume. And that volume is 4/3 pi r cubed, I believe. That's the volume of a sphere. So I'm modeling this as a sphere. So that's some density, not beta. That's some density rho times 4/3 pi r cubed all over r squared. And so what we get is that the force of gravity, if you let the object vary in size, is going to equal some constants, depending on their density, times r, essentially. So it scales with r. That's really important. So if it stretches on, the radius is 3 times as large, that would mean that the force of gravity must equal 3 times the original force of gravity on Earth, which means that the spring must stretch 3 times as far. And the reason we know that is because the force of, in order for it to be, the spring force to cancel out the gravitational force, so for them to be in equilibrium with each other, they must equal each other. And so if we increase the force of gravity by 3 times, we increase the spring force by 3 times, and the spring force is equal to negative kx. So it's linearly proportional. So the force of the spring is proportional to the displacement. So if this goes up by 3 times, then this goes up by 3 times. All right, number 8. 2 springs are attached in parallel. One has a spring constant of 0.4, and the other has 6 newtons per meters. Determine the effective spring constant. If they're attached in parallel, you just add them. So K total is going to equal K1 plus K2 if it's parallel, and that would be 10 newtons per meter. Done. All right. Going back to number 7, this one's a bit more interesting. We got a spring in a mass system put into circular motion. Derive an expression for the radius of rotation as a function of the velocity. So we have the sum of all forces equals mass times acceleration. Now, I was assuming that this was not including gravity. We're not going to include gravity because that's going to change then, depending on where it is on the circle. So this is like in space or something, or horizontal. Doesn't matter. It's just no gravity on this one. And so the only force acting on this object right here is the spring force pulling it in. So we have the force of the spring is equal to the mass times acceleration, the centripetal acceleration. So this is equal to mass times v squared over r. And then we have the force of the spring is kx equals mass v squared over r. Now, you might be like, oh, but it's negative kx. Well, we could just make it the absolute value, kx, and make inwards as a positive force. So we know where it's going. It's going in, and our positive is gonna be positive. So that force is positive then. All right, so just solve for v equals, solve for radius. So that was wrong. solve for radius. Radius is equal to mv squared over kx. Oh wait, but k and x is actually, in disguise, it is r. So actually r squared equals mv squared over k. So then r is equal to square root mv squared over k, or r is equal to the square root of m over k v. Bam. Looks like that. Next. Two blocks are attached by a string and arranged like the image. The table which the 3m mass is on has friction. Determine the minimum static frictional coefficient needed to keep the system at rest. So sum of all forces is equal to 0. And so we have the force of this one pulling down, which is going to be the tension. So we have mg. Let's make that... Yeah, let's just erase that right now and we'll make it negative. So we have the static frictional coefficient, or sorry, the static frictional force minus mg is keeping this thing at rest at 0. The static friction is mu n minus mg equals 0 again. What we got to do is we got to realize that the other direction, so this was in the x direction or something, the sum of all forces in the y direction also equals 0, and that would mean that the normal force must equal 3mg. So we have subset that in there. We have mu 3mg equals mg, so the mg's all cancel. We get mu is equal to 1/3. There you go. All right, this page we did in class, so I'm going to stop there.